Have you seen any of the Ice Age movies? I find them a bit irritating, but my kids really like them. Now, while the movies are pure fantasy in many ways, they also capture some reality, and that the Earth really was a very different place during the last Ice Age. And these recent climate fluctuations are the context for the rise of humans and our increasing role as Earth shapers. Now, we saw this graph before in week 3 when we were looking at how the ocean changed, and specifically how sea level changed in the past. And this graph shows how during the last ice age it was possible to walk from the mainland to Tasmania across a land bridge. Now, the reason there was a land bridge here was because sea level was about 120 meters lower during the last ice age than it is today. And the reason the sea level was so much lower is because a lot of the water that had been in the ocean was actually locked up in ice sheets that covered large parts of northern North America, northern Europe, northern Asia, southern South America, and even parts of Tasmania. So the last ice age started around 100,000 years ago. It peaked about 20,000 years ago, and it ended around 12,000 years ago. This last ice age is part of a longer cycle of ice ages that started around 2.6 million years ago. Now, the last ice age marks an important transition in humans as Earth shapers. So modern humans, or Homo sapiens, evolved between 100 and 200,000 years ago in Africa. And it was during the last ice age, about 60,000 years ago, that Homo sapiens left Africa and spread out throughout the whole of the Earth. And they were able to do so because the low sea levels let them basically walk across large parts of the Earth in between continents, for example, from Asia into Australia. Now, the end of the last ice age, beginning around 10,000 years ago, that marks another big step that humans took as Earth shapers. It marks the beginning of agriculture. And many believe that the warmer and more stable climate of the Holocene, so roughly the past 10,000 years, may have promoted the rise of agriculture by human societies. So this graph shows the temperature in Antarctica over the past 800,000 years. The temperature was reconstructed by analyzing the chemical composition of ice preserved in an ice core from Antarctica. Now, the graph shows several of these 100,000-year cycles, including the most recent one, which peaked about 20,000 years ago. And then you can see the rise in temperature coming out of the last ice age, starting about 12,000 years ago. Now, in terms of human evolution, we see the first evidence for Neanderthals about 400,000 years ago. Then between 100 and 200,000 years ago, we see the rise of Homo sapiens, so anatomically modern humans. And then around 30,000 years ago, the Neanderthals went extinct. Ice ages are caused by tiny variations in the amount of sunlight reaching the Earth, caused by changes in the way that the Earth rotates around the sun. A Serbian astronomer, Milutin Milankovic, laid out this theory, and there's really 3 important variables. The first is the eccentricity of the Earth's orbit, so that's how elongated it is. The second is the tilt of the Earth's orbit, so how tilted it is, basically how extreme the seasons are. And the third parameter is the precession of the Earth's orbit, so that's the wobbling of the Earth around its orbit, around its axis. Now, astronomers can calculate with great precision how these orbital parameters have changed through time and what the impact would be on the amount of solar radiation received by the Earth over time. And what the scientists discovered is that the timing of these orbital changes lines up pretty well with the timing of the ice ages. Now, this graph summarizes the theory. The idea is that certain orbital configurations favor the growth of large ice sheets in the northern hemisphere. Particularly when you have cold summers in the northern hemisphere, you can build up ice in the northern hemisphere. Problem is, the changes in the amount of sunlight reaching the Earth are really minuscule. They're in no way enough to build an ice sheet or to cause the Earth to enter an ice age. So there have to be feedbacks in the Earth system that amplify this tiny initial change in sunlight into a really big change that can cause an ice age. Now, one proposed amplifying mechanism is called the ice albedo feedback. The idea here is that an ice sheet is white and it reflects a lot of sunlight back into space, and that cools the planet, causing more ice to grow, causing more cooling. So that's an example of a feedback process. Another amplifying mechanism is CO2 in the atmosphere. So coming back to the ice core record, we can see that over these glacial and interglacial cycles, every time there was cold temperatures, there was also low concentrations of carbon dioxide in the atmosphere. And CO2 is an important greenhouse gas, as we know. And so the low CO2 concentrations in the atmosphere during glacial times were really important in cooling the planet through sort of a reverse greenhouse effect. Now, to put these CO2 changes into context, recently, CO2 concentrations in our atmosphere climbed above 400 parts per million. And we can see that in the context of the past 800,000 years of Earth's history, 400 parts per million is really extraordinary. So the changes in CO2 that we're experiencing now are on the same order of magnitude of what the Earth experienced between an ice age and an interglacial period through earlier parts of Earth's history. Now, exactly why the CO2 was low during glacial times is a real mystery. In fact, this is something that I'm working on right now. Now, one proposal for low CO2 during glacial times was proposed by the American oceanographer John Martin. His idea was that during glacial times you have an expansion of desert areas, and this would deliver more dust to the ocean, and dust contains a lot of iron. And John Martin's idea was that in many parts of the ocean today, the growth of single-celled plants in the ocean called phytoplankton is limited by iron. They're anemic and they don't have enough iron to grow. So if they receive more dust from the deserts, that would add more iron and would enable these phytoplankton to grow prolifically. Now, phytoplankton, when they grow through photosynthesis, they take up carbon dioxide from the atmosphere. So the idea is that these phytoplankton are acting as little carbon sponges, sucking up carbon from the atmosphere, stuffing it into the deep ocean, and lowering CO2 concentrations in the atmosphere, which would cause more cooling, expansion of the deserts, and more iron going into the ocean, and so on. So that's another feedback process that could be causing low CO2 concentrations during glacial times. Now, the ice core record supports John Martin's hypothesis. We can see that during those ice ages, when we had low temperatures, low CO2, there was also a lot of dust reaching Antarctica and also reaching the oceans. So this supports John Martin's idea. Now, more recent work, including work that I've done, shows that while it's true that we do see evidence that there was more ocean productivity during glacial times, we can see now that that change alone wouldn't be enough to get us to the very low levels of CO2 that we see in the atmosphere during glacial times. To get to those really low levels, we need to invoke other changes in the Earth system, in particular changes in the ocean circulation. Now, the field of paleoceanography is really critical for testing these hypotheses of how the ocean responded to and contributed to past climate change. Paleoceanography involves studying sediment cores recovered from the bottom of the ocean. You can see an example here in the bottom left of the graph, and we can analyze the chemistry, the microfossils, and the geology of these sediment cores to try to reconstruct how the ocean changed in the past, and that can give us some insights into how the ocean might respond to future climate change. So now that you've had a quick tour of the ice ages, I urge you to learn more about the ice ages by exploring a couple of the resources we have on the Milo page. The first is an ABC feature with Dr. Stephen Phipps, an ice sheet modeler from UTAS. And the second is a great timeline feature that lets you explore human evolution within the context of climate change, including the ice ages. And I urge you to use the magnifier feature on that website, which lets you see some fascinating evidence for different stages of human evolution and how they tie into climate change. So that's all for me. Thanks for listening, and I'll see you later. Bye.